Okay, so my name's Neil Sinclair. First and foremost, for I guess this event, I'm the secretary of the Incosi Automotive Interest Group, which Stephen and a couple of other presenters are part of. I'm also a consultant for System Forge, and I've got one more hat. I'm also an associate consultant with Scarecrow Consultants and another, which are MBSE consultants. So today what I'd like to do is just take you through the complexity challenge that the automotive industry has sort of found itself in over the last few years, and give you an appreciation of just how complicated that's becoming, and also to give you an idea of how model-based systems engineering could help the situation and could actually provide quite a sort of an answer to some of the challenges that the automotive community, especially OEMs, are currently facing. So not so long ago, cars were relatively, I'd say relatively simple things, predominantly mechanical devices, with the purpose of going from A to B, and in this case an old Porsche, probably as quickly as possible. And the organisations that grew up around that, if you like, in automotive companies, they were able to, if you like, focus their organisations around certain competencies such as powertrain, body and trim, electrical, chassis, that kind of thing. Because cars, a lot of these areas were relatively, they were disconnected. So you know, for instance, a wiper system would be some form of switch, an electric motor, a gearbox, some form of mechanical kinematics to wipe the window. But apart from having some power supply to it, it was pretty much isolated from the rest of the vehicle. And the same goes for a lot of these other systems within the vehicle. But over the last 10 years, we seem to have had, as we've evolved into new vehicles, you know, even today, the primary purpose of the vehicle is to go from A to B. However, what's actually happened is new technology has come along, which the automotive industry has adopted and added in to their current organization and product creation process. So some things you may recognize here: head-up displays, automatic emergency braking, adaptive cruise control, blind spot detection. All these kind of things have been added in to the vehicle, and really, you know, from the vehicles haven't really changed. Most of them have got four wheels, they have an internal combustion engine. But what's actually happened is the industry has added all of these new features to address their customer needs and to make the vehicles safer. And also what's happened is, of course, we've started to get interaction with things that are not on the vehicles, such as, you know, receiving GPS information. And also now recently, we're starting to get a kind of new functionality. There's a lot more connectivity. So all of these things are connected. And in actual fact, the thing that, apart from all of these things, but having some form of connection or interface, behind all of this is a whole heap of software, which is arrived, which is delivering probably 80% of what or contributing to 80% of what a driver or experiences within the vehicle, from how the car handles to how information is supplied to the driver, or, you know, how they might, you know, just use Google CarPlay or whatever, Google and CarPlay. So there's a whole heap of things that happen that made things really quite complicated. Yet the organizational construct and the general approach to developing cars hasn't really changed that much. And we've got some new things that have arrived, such as electrification, which might remove the parts count, but increases probably, or certainly adds a certain level of complexity and new technology. And also now we've also got this idea of autonomy, so autonomous vehicles, which is a direction that most OEMs want to go. Driving some of this as well is because now these cars have some more automatic features. There's a level of certification and type approval that is required by industry and by governments in order to allow vehicles to actually drive on roads. And while certification has been around a long time in the aerospace industry, aerospace and defense industry, the kind of rigor that's required here in the automotive industry is relatively new, and that's another added complexity to the whole challenge that the automotive industry has got at the moment. And then, as we've seen from the previous presentations, the car then will start interacting with the road infrastructure, and also we're delivering more services from off the car directly into the car. So things have got complicated pretty quick, and suffice to say, it's a big challenge for car companies, and the evolution to the kind of car company, I guess, that they need is still in progress. So, I mean, what I think I've shown you is project complexity is going up. The number of disciplines on functions in the vehicle is going up. I guess the issue we've got is that while we have some very clever engineers, the evolution of engineers' brains is maybe not evolving as fast as the complexity. And human beings can probably hold together 5 to 7 interrelationships if they're trying to solve a problem. But beyond that, it becomes almost impossible to deal with. So most, even a somewhat simple function has a lot of interfaces and a lot of interaction with a lot of different things in the vehicle, and somehow we need an approach that's going to allow engineers to do good engineering, focus on the essential things that they need to focus on, and be able to deal with all these different new interrelations that they have to deal with. Generally, in the automotive industry, a complicated problem, and with short time scales, the main approach was to add more brains. So which is great if the product is relatively simple. But now we've got the complexity added. Adding more brains just adds to the complexity. So we have to think of something slightly different, to different approach in some ways to developing cars in order to be able to address both the short timescales that the automotive have, but also the complexity that we now face. The other thing is that there's been a bit of a shift in how vehicles are conceived. Because vehicles didn't change for a long time, it was very much sort of a bottom-up approach. We knew what a vehicle was. It had 4 wheels, it had an internal combustion engine, and the automotive industry tended to find new technologies and bolt those Lego bricks into an existing concept. But recently, other people have arrived on the market, such as Tesla, who've got a slightly different approach. They tend to do a top-down. They tend to say, this is the kind of vehicle we actually want, or concept, or this is the problem we're trying to address, and what stuff do we really need to build or put together in order to achieve this, which is slightly different than the approach of some of the more traditional OEMs. So that's another problem. Now, systems engineering, which I guess we're all familiar with, has got there's different interpretations of what systems engineering is if you go on the internet. But in essence, what we're trying to do with systems engineering is we're trying to define the whole problem that needs to be addressed. And we're trying to make sure that the whole system that we design and evolve will address that whole problem, and that whole problem will address the stakeholders' needs. And we also need to address the whole life cycle, because the other thing that's changed for automotive companies is, and Tesla did this really, and gave them a bit of a shock, the old OEMs, is basically. Previously, car companies would sell a vehicle and pretty much they were done. So beyond the point of sale, there was no more development and no more new functionality that was going to be put in that car apart from fixing the recalls. However, Tesla are now putting new functionality into cars beyond the point of sale to delight their customers. And that's something that we, standard OEMs, old OEMs, need to start to deliver. And there needs to be a way of doing that. And one of the ways that we can do that is if we're considering the whole, I'm just trying to get some things off my screen. If we're considering the whole life cycle of the product, and that's what we're trying to do with systems engineering. Systems engineering started in the aerospace and defense industry. There's a bit of debate about when it actually started, but the late 50s, early 60s. And predominantly it was a document-based approach that was used to define the requirements and then decompose those into sort of functions and then components, and then do the validation. Holt and Perry, you may or may not know, in their very large tome, model-based approach, SysML for systems engineering, talk about three evils that we're trying to use systems engineering to avoid. One is, I guess, unnecessary complexity, which comes in two forms. There's essential complexity, which a product needs to have in order to be what it is. But there's also a lot of accidental complexity. If we don't know how all the parts of our system relate to each other, and we don't know the interfaces, then we quite often get slightly, we have some surprises, I guess, when certain bits of complexity turn up late in the life cycle that you hadn't actually anticipated were actually related, and this can cause all sorts of issues. So one of the things we need to do is focus on the essential relationships and complexity, and remove the accidental complexity. The other thing that they quite rightly point out is that quite often there isn't really a common language. So across the development of a product, we don't really have defined the language and the terms for those system elements. And therefore people have different interpretations, and different stakeholders have different interpretations of the meaning of certain elements. And therefore one of the clear things that we need to do is define some form of common language, and we need to be able to make sure also we address all the stakeholders, not just the stakeholders that the component owner, for instance, thinks he's addressing. Because quite often the stakeholders there are more stakeholders, and probably different stakeholders than you originally thought when you tried to address that problem. And the other one is around lack of understanding. So from again, Holt and Perry, we should really be trying to address the whole system. We should be trying to address it across the life cycle, and we need some way of doing that. Now, previously I mentioned that systems engineering started as a document-based approach. But more recently, people have started to move towards what they call a model-based approach. And I'm going to try in the next few slides to give you a high-level overview of what that actually is. So really what we mean by a model-based approach is what we do is we try and abstract the system of interest into a model. In other words, we try to understand what the essential relations are between these system elements, and we try to focus on those, and we try to remove any accidental complexity within that we might see. And the model needs to be abstracted at a level that we can work with, but one that I suppose produces meaningful results. So there's this concept of model-based systems engineering is we would, for instance, look at how we develop a car, and we would define how requirements were related to vehicle features, which were related to functions, which are related to components, for instance, and we would model those. Now, the modeling notation that you use it can vary, but currently the industry seems to be focusing a bit like the aerospace and defense area around SysML, which is a modeling notation. And the great thing about that is not only can we start to model our system, abstract our system in a model, but we can also get technology, in other words, tools to help us with that, to manage the complexity. So a model-based approach means that we take that system, we abstract it, we use some method or language that we determine, and then we can use a notation such as SysML to be able to model that in a way that allows technology to help us. But the important thing is with model-based systems engineering is that model probably is already complicated in itself. And so what we need to do is we need to take related elements of that model and effectively with the relationships that we've already defined and provide stakeholders information in the context that they need to consume or create that information. And generally, with a model-based approach, it's generally through diagrammatic approach, such as sequence diagrams and structure diagrams and state machines and this kind of thing. That doesn't necessarily mean that when we're using a piece of technology in here that we need to communicate with all our stakeholders that way, because some may be interested in, I don't know, Word documents or that great engineering tool, Excel. And if we use the right technology, then we can actually take this information and we can communicate with them through the medium that they're most comfortable. But the most important thing here is what we've actually done is we've taken a model, we've taken the system, we've abstracted it, and then we've made, if you like, we now have clear understanding of the relations and definitions of the system elements so that then we can manage the complexity. So what I wanted to do was very quickly, in a simplified way, just give you run you through that. So if we have a system that comprises of A, B, and C, and we implicitly understand these elements. So for these could be any system elements, but for this, let's just take this as requirements. So requirement A, requirement B, and requirement C. We might understand requirement A implicitly at an atomic level. We might understand B and we might understand C, but we actually don't really understand the system because the A, B, and C all have interactions with each other. And actually, the interactions make the system quite complicated. So just understanding each individual at atomic level doesn't really describe how the system works or what its behavior actually is. So with model-based systems engineering, what we try to do is understand what those relationships really are and model those, as I showed you before, in a kind of a model and usually using a tool. And the great thing about that is that the stakeholders that we've identified, they don't have to deal with all the complexity. So what we can do is we can provide them the information in the context that they need to either input or consume. And it allows us to manage that complexity. And on the back of that, we also, because we modeled our system, we also have that traceability. So to deal with the legislative and certification elements of which are challenges that automotive companies have, we can actually use the model to prove that kind of traceability to the right authorities. So this is the idea of model-based systems engineering. We take a system, we abstract it, we create views for the context of the consumers, of the stakeholders, and we also make sure those views are consistent, and the views are consistent with the model, and the model which is consistent within itself in terms of terms and relationships. So really that's a very, very high level, I guess, view of model-based systems engineering, and hopefully you've got an idea of the challenges maybe that the automotive companies are facing. And I think really you should take this as just a high-level context, because in the next presentation from Ian Cunningham, he's going to take you from a sort of a model-based approach into a real hard data model for vehicles. And hopefully this is just giving you an idea for what this concept of model-based systems engineering is. So most automotive companies are going down this road. I think probably the system of systems, which is the road infrastructure and off-car services and that kind of thing, probably would also benefit from a model-based approach. It's a way to address the complexity and manage it, because at the moment there doesn't seem to be any other anything out there that will help us address the complexity, which is gone to it's quite extreme at the moment, and we need to be able to manage that with the help of an approach, which is the model-based bit, and hopefully with some technology as well that can manage the interrelations in the model and understand the changes and the information and relate those across the whole of the complex model.